In Chapter 16, Section 7, we're going to look at surface integrals. So we have, in the first problem, a surface integral of a function x plus y plus z with respect to a differential line segment S, and then we're given parametric equations to replace this with. So it says x equals u plus v, y equals u minus v, z equals 1 plus 2u plus v, and then it gives us bounds on u and v. So to do this problem, we're going to use this general equation. We're going to have this equation, the double integral of s, it's a bad s, of a function of x, y, and z with respect to s. We're going to change that to a double integral over some region D of the function of this vector r that's in terms of u and v, the parametric parametric representation of vector r, then times the magnitude of the cross product of partial r with respect to u and partial r with respect to v. And that's going to get us dA. And that's pretty much what we're going to do for most of the problems in this section. So we're going to have our function is going to be, we have in this problem, x equals u plus v, y equals u minus v, and z equals 1 plus 2u plus v. So ru, the partial derivative of r with respect to u, is going to be, it's just the partial derivative of these three equations with respect to u. And I'm going to write it in compact vector form. So the partial derivative of x with respect to u is 1. The partial derivative of y with respect to u is 1. The partial derivative of z with respect to u is 2. So anything that's not a u goes away, and anything that is a u, it's just regular derivative rules. 1u derivative is 1, 2u the derivative is 2, etc. Rv, the partial of r with respect to v, is going to be same three equations. Take the partials with respect to v now. Partial x with respect to v is also 1. Partial y with respect to v is minus 1. And partial z with respect to v is positive 1. So we have those three. Now we have to take the cross product of these two things. So that's going to be I, j, and k. And we're going to have ru first, 1, 1, 2. Rv second, 1, minus 1, 1. And it's going to be cover up the I column, then do a 2 by 2 determinant of 1, 1, and 2 minus 1. So it's going to be 1 minus minus 2. That's in the I. Then it's minus, cover up the j column, the middle column. It's going to be top left 1 times bottom right 1, which is 1, minus top right 2 times bottom left 1, which is 2, in the j, plus, notice the alternating here. First bubble is plus, second bubble is minus, third bubble is plus. We've done this before, but it doesn't hurt to remind you. Cover up the third column k, 2 by 2 determinant, those 4 ones on the left side. It's 1 times minus 1, minus 1 times 1 in the k. So if we do this, we get 3. Minus 1 with another minus is positive 1, and then minus 2. So that's Ru cross Rv. Okay, now we need to find the magnitude of this vector, which is just the square root of the sum of the squares. So it's 3 squared plus 1 squared plus minus 2 squared, which is going to be the square root of 9, plus 1 is 10, plus 4 is 14. Okay, so we've got probably the hard part of this done. Now we're going to replace this function xy plus z with its u and v components. So we're going to say x plus y plus z is going to equal u plus v, which is x, plus u minus v, which is y, plus 1 plus 2u plus v, which is z. So we can see that these three things are x, y, and z, which is what the function is, x plus y plus z. And we can see that these will simplify. Let me use some space up here. We've got 2u's plus another 2u's, so you got 4u there. This v and this v will cancel, and we've got plus 1v over here, and we have plus a 1 right there. So that should simplify to 4u plus v plus 1. So we can set up our double integral. And I think they told us somewhere in this problem that u is going to vary from 0 to 6, and v is going to vary from 0 to 1. So I think I did du dv, so it's 0 to 6, 0 to 1. And it's 4u plus v plus 1. Now that is this part times the magnitude, which would be root 14, and then it's du dv. Okay, so we're going to get, pull the square root of 14 out front, and then we can just take the antiderivative of each of these terms with respect to u. So this is going to be 4u squared over 2. If it's just v, it now gets a u on it, uv plus the constant 1 would get a u on it, and it's going from 0 to 6. And if we do that, how much of this do I want to show? You're going to get square root of 14 on the outside, 0 to 1. When you plug in 6 for u here, and 0, which will just kill all those terms off, but if you plug in 6, you should get 78 plus 6v dv. And that's a fairly simple integral. It would be 78v plus 6v squared over 2 from 0 to 1. So we're going to get plug in 1, you're going to get 78 plus 3 times the square root of 14, which is 81 square root of 14. So that is the surface integral of a parallelogram with parametric equations given between those values for u and v, for problem 1. And that's basically how we're going to do most of these problems. We're going to switch them to u and v, parametric, take a cross product, magnitude of the cross product, replace the equation with u's and v's, and then do our double integral. Problem 2, very similar. They give us this parametric vector r with u and v in it right away, and it's u cosine of v, and it's u sine v, and then it's v. Well, that makes it pretty easy to get ru, which would just be cosine v, the u goes away, sine v, the u goes away, and 0. So the partial derivative of v with respect to u is 0. Then rv is a little more complicated. The derivative of cosine is minus sine, so this is minus u sine v. The u is a constant in this case. Partial derivative of sine v with respect to v would be cosine, so the u is there for the ride, cosine v, and then partial v with respect to v is 1. Okay, and then we have to do a cross product of these two. I think I'm going to skip that part. Showing you one cross product is hopefully enough to refresh you on how to do it. Ru cross Rv from those 6 things should turn out to be sine v negative cosine v and u. And then the magnitude of this, so if you square all those terms, add them up and take a square root, you will get, let's see here, sine squared v, then minus cosine will become plus cosine squared v plus u squared. But these two are our old Pythagorean identity of trig. Sine squared plus cosine squared is 1. So the magnitude of the cross product is just the square root of 1 plus u squared. Okay, and that is going to replace, I suppose I should write our equation somewhere. We're trying to do the double integral over region D of the function, replacing any x's and y's with u's and v's, and then multiplying by the magnitude of the vector ru cross rv dA. And we just found this part. So that part's done. Now we need to replace the function with r, the parametric equation r that's in terms of u and v. The equation is just y, it's just one letter. So what we're going to have is the double integral of y, but y would be this term here. So replace that y with that, we're going to get u sine v. And then it's times that magnitude of the cross product, which is 1 plus u squared. And let's actually put in our limits and do all that. I found if you do du first, then dv, it works pretty well. U goes from 0 to 1. V goes from 0 to pi. So to do this du, you're going to use u substitution. It's kind of interesting doing u substitution on something that has u in it already. So maybe you want to use a different letter, pick whatever letter you want. But basically you're going to say that, if I pick u to be 1 plus u squared, the derivative is 2u, and you can get that u to go away. I'm just going to jump to it because we've done plenty of u substitution integrals. You should get, actually, this is an even better way to do it. You can split these two up. So since this is totally separate from the u stuff, you can separate that into its own integral, 0 to pi, of sine v dv. And then you can just multiply that by, from 0 to 1, u times the square root of 1 plus u squared. Might be a little easier to see it that way. And if you do this, you will get, let me stick with blue since I've got it handy. The blue one will be 2 root 2 over 3 minus a third when you plug in 0 and 1. And the red one is going to give you kind of a simple result. You should just get 2. So that whole thing is going to simplify to 2. And when you combine like terms, or I should say use this lowest common denominator to multiply by 2, this whole thing will simplify into, I guess there's not much you can simplify it into. You'll factor out a common 2/3, and you'll get 2 root 2 minus 1. And that would be the result for this surface integral for problem 2. Problem 3, we're going to actually do a little differently. We're going to use an old form that we've done before, and that was this one. We're going to take a double integral of the region S, no, not S, D, of f of xy times the derivative of 1 plus partial f with respect to x squared plus partial f with respect to y squared. So this was something we saw when we first introduced line integrals, and that's with respect to dA. So in this equation we have z squared, which is z squared equals x squared plus y squared. But we need to write that as z, which is going to be our function of x and y. So we just have to take a square root of both sides and get z is the square root of x squared plus y squared. Okay, then we are going to say, let's see here, so we've taken care of this, and it says it lies between the planes z equal 2 and z equal 3. So we're going to sit on that for a while. We're not going to use that right away. The function is x squared z squared. So this is going to become the double integral of d. The function xy is x squared times z squared, but we're not going to use z, so we're going to write this all in just two variables, x and y. So instead of writing z squared there, we're going to write this. Z squared is x squared plus y squared. Then we're going to multiply that by the square root of 1 plus the partial derivative of f with respect to x. Now this is quite involved. I'm going to kind of jump to the answer. It's going to be x over the square root of x squared plus y squared. Squared. So if you have, you'd have to write this like x squared plus y squared to the 1/2 power. The derivative of that, you bring the 1/2 down, subtract 1, so it becomes minus 1/2, which puts this whole bubble in the denominator with the square root symbol on it. And then you take times the derivative of the inside, which is 2x, and that 2 in front of the x cancels with the 1/2 out front, so you're left with an x on top over square root. Plus, the exact same thing is going to happen with dy dx. It's going to be y over square root x squared plus y squared squared dA. Now this is going to be x to the 4th plus x squared y squared. Now this is kind of interesting. What we get here is 1 plus square top and bottom. You're going to get x squared on top and x squared plus y squared on the bottom. The square root symbol goes away. On this one you get y squared on top and x squared plus y squared on the bottom. The square root went away. Well, those have a common denominator, so you can add those two numerators. So we get d x4 plus x2y2 square root of 1 plus, write those two numerators, x squared plus y squared, over the common denominator, x squared plus y squared, and that whole fraction is 1. So this whole square root becomes 1 plus 1, which is square root 2, which we're going to pull out of the entire integral. So that whole square root becomes square root 2, and we're left with x4 plus x squared y squared. And I'm thinking now I might not have wanted to actually distribute the x squared. Let me see. Get too far off the rails here. I did not want to do that. Okay, so what we want to do instead is we want to go back to before I distributed the x squared. You'll see why we want to do this in a second. Call this x squared times x squared plus y squared. Well, we're actually going to replace this with polar coordinates. So we're going to replace x with r cosine theta, and we're going to replace this with r squared. So if you recall polar coordinates, r squared is x squared plus y squared, and x is r cosine theta. So we're going to get the square root of 2. X is r cosine theta, so if I square that, we get r squared cosine theta squared. And then that's times r squared. And then, because of polar coordinates, we pick up an r, a dr, and a d theta. And let me see what order I want to do this in. We want to do this in, shouldn't matter. In fact, we can split this up because it doesn't matter. If you look at this, z squared, right back here, z squared is r squared. Therefore, z is really r. So this is saying r goes from 2 to r equal 3. Those are going to be the bounds on our r. So I can write that for these, 2 to 3. And then theta is going to go for the full 360 revolutions, so it's going to be 0 to 2 pi. But then I'm going to split this up and call this square root of 2 from 0 to 2 pi of just cosine squared theta, d theta. So this is just like we did in the last problem, times from 2 to 3 of r to the squared times another r. So if you count them, there's 1, 2, 3, 4, 5 of them. R to the 5th dr. I don't need to do the square root of 2 in front of that one because I'm multiplying all these three terms together. So 1 square root of 2 will do it. And did I write these down? You should get out of each of these. Okay, so you get square root of 2 out of this integral, which I trust you can do, you will get pi. And out of this integral, which I trust you can do, you'll get 665 over 6. And if you cram all that together, you're going to get 665 over 6 times the square root of 2 times pi. So just cram those together, and that will be the result for problem 3. Okay, in problem 4, we've got this surface integral of x squared z plus y squared z, where s is the hemisphere, x squared plus y squared plus z squared equals 9. So this is a sphere. So we're going to think spherical coordinates. And in spherical coordinates, your r vector, which will be a function of phi and theta, is equal to rho, which is the radius of the sphere, times, let's see where I have this right now, times sine phi cosine theta, rho sine phi sine theta, and the z term is rho cosine phi. So that is what r would be, and the only thing we know is phi. Phi is going to be 3. So if this thing equals 9, that's phi squared, which means phi has to equal 3. So this 9 tells us what the radius of the sphere is. So our r is pretty similar. It's just going to be 3 sine phi cosine theta, 3 sine phi sine theta, and 3 cosine phi. Just like before, we need to find r phi and r theta. So r phi would be the partial derivative of this vector, only considering phi as my variable. So we're going to get 3 cosine phi, derivative of sine phi, times cosine theta. And this one's going to be also 3 cosine phi sine theta. And this one's going to be minus 3 sine phi. Then we're going to find r theta, which is the partial derivative of these three terms, only considering theta. So it's going to be minus 3 sine phi sine theta. It's going to be 3 sine phi cosine theta. And this one's 0. So the partial derivative with respect to theta of the last term is just 0. And then we're going to take their cross product. So we're going to take if you take their cross product and take their magnitude, so I'm kind of skipping a few steps here, you should get, for this problem, 9 sine phi for my numbers. So again, the cross product, you're going to have to take these 6 terms, cover up the columns, do the determinants, and then for the magnitude, you're going to square root take a square root of the sum of all those things squared, and you'll get some cosine squareds plus sine squareds. That'll become 1. You get some stuff to drop away, and you'll have at the end just 9 sine phi. The reason I did that is because this double integral is a bit involved. So if we take the double integral of s of x squared z plus y squared z ds, we have to write that as, trying to think if there's a shortcut here. Not really. We have to write this in terms of phi and theta. So anywhere we see an x squared, this whole, let me use this one. This whole thing is x, this whole thing is y, this whole thing is z. So we have to replace x squared with 3 sine phi cosine theta squared. So that term right there, I think what I did do, just to save a little bit of work, was this. Okay, let's factor out a z here. X squared plus y squared times z ds. So let me actually pick it up from there. So let's just do x squared plus y squared. X squared is going to be 9 sine squared phi cosine squared theta. So I'm squaring absolutely everything in that x term, plus now square everything in the y term, 9 sine squared phi sine squared theta. Okay, that's x squared plus y squared times z. Z is 3 cosine phi, but it's also times this. So what we're doing here is we're writing the double integral of the function in terms of the radius vector of phi and theta, which is all this stuff. So everything I just wrote is just that part. Then it's still times r phi cross r theta. And then in polar coordinates, not polar, in spherical coordinates, we pick up a d phi d theta. So we've just written, all this is just the first f of r. Now we need to add this component, which is 9 sine phi. So it's times 9 sine phi. Then we pick up our d, let me make sure I do the same order so I don't have to rethink this. Yep, d phi d theta. D phi d theta. Okay. Now one thing we're going to notice is that there's a common 9 sine phi in both these terms, sine squared phi. We're going to factor that out and we're going to be left with cosine squared and sine squared, which is going to be 1. So that whole double term bubble is going to reduce to just 9 sine squared phi. So we're going to get, maybe I will show that intermediate step. We're going to have double integral of just 9 sine squared phi times, let's combine this 3 and this 9 and call this times 27, and we have cosine phi sine phi. Let me write it as sine phi cosine phi, and that's d phi d theta. We can actually combine this 9 and 27, and we can combine this sine phi and sine phi because it's all being multiplied. So we're going to get 27 times 9 is 243, is that right? So we're going to get, and let me do another thing here. Let me split these up. So because these phi's and these cosine and these thetas are completely independent, actually I don't even see a theta. Did I make a typo? No, there's no theta at all. So this can be split up pretty nicely. We're going to write this as 243, that's 9 times 27, sine cubed of phi times cosine phi d phi times antiderivative of just d theta. And phi in this case is going to go from 0 to pi over 2, and theta is going to go from 0 to 2 pi. And for this one, you have to break sine into 1 minus cosine squared theta, phi, times the sine. So you break sine 3 into sine squared, and you make the sine squared 1 minus cosine squared, and then you can call u cosine, which the derivative is sine, and you can do a u substitution. We actually did a problem very similar to this in a previous homework. And let me just see here. So if you do this, this whole thing is going to reduce to just 243 over 2 times pi. So you get quite a bit of things to simplify in that once you do those antiderivatives for problem 4. Okay, in problem 5, we're going to use something we talked about in maybe a section or two ago, and that was if we have the double integral of s of f dot ds, that's going to equal, we'll get the double integral of the surface S of the field dotted with the normal vector to the field ds, which can be shown, I'm not going to show it, but it can be shown that this can be simplified to over the region D of minus P dg dx minus Q dg dy plus R dA. Okay, so we're going to pick up with that, and they told us the vector field, this is called flux, so these equations give us the flux of this field, vector field. The flux for this one, actually the vector field for this one, F, in x, y, and z is, I'm going to write it in compact form, xy, 12x squared, and yz. And those are P, Q, and R. So we had seen those, finding P, Q, and R in a previous section. Then we need, so we have P, Q, and R. Now we need dg dx and dg dy. Well, z, whatever that is going to be our g function with respect to x and y. And they gave that to us in this problem as xey. So dg dx is just going to be e to the y, and dg dy is going to be x e to the y, same thing. So we know all 4 things, or 5 things I should say, and we can plug them into this double integral. We just need to know how our x's and y's vary, which they also tell us. And what order of integration works best? Looks like doing y first is best. So we're going to write this as dy 0 to 3, dx 0 to 1 from down here, of negative p, which is going to be negative xy, times dg dx, dg dx is ey, minus q, q is 12x squared, times dg dy, which is times xey, then it's plus r, according to this formula, r is y times z. but we're not going to use z because we don't want z's in any of this. So we're going to instead use what z is. Z is xey. So this is y times xey. And we're doing derivative of y first and then x. And let's see, is there more simplifying I want to do here? We're going to get, it looks like you can simplify this to be 0 to 1, 0 to 3 of simply negative 12x to the third e to the y dy dx. And if you do the first integral with respect to y and plug in 3 and 0, you're going to get negative 12 e to the third minus 1, that's the y, ey being 3 and 1, 3 and 0, then the x cubed, then the dx. And if you take the antiderivative of that and plug in 0 and 1, you should get, at the very end, when you combine like terms and simplify, negative 3 e to the 3 minus 1. And I think I just distributed this minus 3 to get to this point here. Okay, so there are a few steps I skipped there. You can see that, actually this one might be easy to see, this first part. Minus xyey and plus xyey, those two are going to cancel, and you're just left with this. This x to the 1 combines with this x squared, and you get x3. You're left with this right here. And then the antiderivative of this with respect to y is easy. It's just ey. It's the same thing with everything else there. And then y is in 1.3, and then it becomes 0. But when y is 0, e to the 0 is 1. So this would have been e to the 0 here to get that. Okay, and then when I take an antiderivative of that, up here. And then all this is constant. So minus 12, e3, minus 1, it's all constants you can just pull out. So it's really just the antiderivative of x3, which is x4 over 4. And then when I plug in 1, you just get 1/4. 1/4 of 12 is 3, and that's it for problem 5. Okay, 6 turned out to be a little more challenging than I wanted it to be. It's really involved. You have to set up 6 separate integrals like this. I'm going to talk you through it, but I don't want you to actually do this. I don't expect you to do this problem. If you do it, we'll give you a bonus point, but if you don't do it, I'm not going to count that against you. So let's say you don't do it and you get a 0 in WebAssign. That's what it looks like. At the end of the course, I won't do it for everyone because I'd have to go into 30 students and say +1, but at the end in my Excel worksheet, which is much easier, I will add a point back in to every student for this problem. So if you do it and get it right, I'm adding another point on. That's where the extra point comes in. Okay, but I will show you what they are trying to get at with this problem, and then you can see my answer, and maybe you can work backwards and figure out how to do it. So they want us to do this double integral of this surface in a vector field and the flux and all that stuff. So they give us f, which is easy enough. The flux wouldn't be terribly hard to find, but the problem is they want you to do it for a cube. And this cube has vertices of +1, -1 in all 3 dimensions. So if you do this, you're going to end up with, now that I'm looking at it, I'm wondering if my drawing is off. I think it is, the way I drew it on my notes. So let me correct that. So its vertices occur at +1x, oops, I forgot a line. And -1x, +1y, -1y, +1z, -1z. So this is going to be a cube that looks like this. Okay, so I wanted to draw that while I had the video paused because it's a mess. It's hard to draw. So this is the cube formed by having the vertices at +1, -1 in the x, +1, -1 in the y, +1, -1 in the z. So it's like centered right on the three-dimensional axis of all these octants in 3 dimensions. And then what they want you to do is they want you to say, okay, and maybe I will just show you one. So they say surface 1 is going to be the front-facing surface. So it's this surface in purple that's facing us. So that's called surface 1. And again, you'd have to do this for 6 surfaces. So there's surface 1 in the front, then 2, then 3, then 4, and then the top and the bottom. So they're going to say, let's see here. Let's write our vector. So our field XYZ is equal to, in compact form, X 4Y 2Z. Now that's P, Q, and R. And then our Z equation, our f of x, actually in this one, don't do that. So use the simpler, maybe simpler. It's going to be double integral, let's see how I wrote it. So use this form of flux, S vector field F dotted with the normal vector N ds. Because it's pretty easy to figure out what the normal vector would be for this 6-sided cube. So the normal vector for this cube right here, imagine putting a dot right in the center, is going to go this way. So it's going to go away from this surface, and it's pointing in the x direction. So the normal vector is just 1. It's basically I. It's pointing in the x direction, and then it has zeros in these other dimensions. And you can see each of these faces is going to point either in positive y or negative y, positive z, or positive x, negative x. So they're all going to be really simple vectors like this. And then when I dot these, you're going to get these zeros for these terms. So for this surface, we're going to get, now there is a little bit more involved than just taking a straight dot product here. Without going into the more expansive formula like we showed before, there's one more thing you have to do, and that is you have to transform f into one where you take a partial derivative with respect to whichever surface you're dealing with. So if we're dealing with this surface that's pointed in the x direction, we take a partial derivative with respect to x of the first term, so that would be 1. And we can leave these other ones alone. And that's what we'll dot product. So we basically get the dot product of these two things, that f and n ds would equal, it's just going to be 1 plus 0 plus 0. Actually, I don't need a vector sign because dot product of two vectors is a scalar. So we get integral, and it's dy dz. So we don't even take this integral with respect to x because that is along in the x direction, nothing's going on. It's in the y and z directions that things are changing. Okay, so we would go from -1 to 1 and -1 to 1 for both of these. And we get dy dz. Well, this is pretty simple integral to do. For my numbers, it's just going to be 4. Okay, let me show you how the setup would be for surface 2, which I believe is right here. So this is S2. And clearly the normal vector is going to point along the y-axis, positive. That's the normal vector. Oops. I mean, it technically is a unit vector, so I could use a hat if I wanted to. Okay, so in surface 2, the field vector is going to be equal to x, partial derivative of 4y is 4, 2z left alone, and then the normal vector is going to be 0, 1, 0. So the double integral is still minus 1 to 1 of, if you take a dot product of these two, you're only going to get 4 to survive. So it's 4, and now it's dx dz, because in the y direction nothing is changing. And what we get is, when you take this integral, it would just be 4x, and then plug in 1 and minus 1, and you'll get 8, and then it becomes 8x, plug in 1 and 1, you get 8 plus 8 is 16. And basically you go and you repeat this 4 more times for the other 4 surfaces, and you get 4 more numbers, and you just add those 6 numbers up, and that is the total flux along this cube. A lot of work for this problem. Again, optional. If you want to do it, you can get a bonus point. If you don't do it, you'll still get credit for it. Okay, 7 is not as bad, so let's look at that one. We have the vector field equal to xz e to the y in the I direction minus xz e to the y in the j direction and z in the k direction. And we have S is the plane x plus y plus z equal 9. So we're immediately going to solve that for z and call it the function g. Would just be 9 minus x minus y. And we're going to call this term p, this term q, and this term r. And so we're going to get the double integral over d of, basically it turns out to be negative p dg dx minus q dg dy plus r dA. So we get minus p would be minus xzey times dg dx. Now this is a very simple formula. The partial derivative of 9 minus x minus y with respect to x is just minus 1. Then it's minus q, which is a minus xzey. And then it's going to be times dg dy, which is also minus 1. Then it's plus r, but r is z, but we're not going to use z. We're going to use 9 minus x minus y. And we're going to do this derivative with respect to, let me stay consistent with my notes. So d looks like I did, shouldn't matter in this case. I think they're both pretty simple. No, it doesn't matter. dy dx. And we'll see why it matters in a second. Okay, so if we look at this, we're going to get, this is going to be positive, this whole thing is going to be positive xzey. This whole thing has a triple negative, so this one's negative xzey. So those two terms are totally going to kill each other off. We're just left with this term. So the double integral is going to be 9 minus x minus y dy dx. Now the limits we have to get from, let's see here, from thinking about z. So it says in the first octant, so if z is 9 minus x minus y, if we imagine in the first octant, the way that's going to look is a straight line when z is 0, and the line is going to be described by 0 to y equal to 9 minus x. So basically from here, we get two constraints. One is x should be between 0 and 9. The other one is that y should be between 0 and the line 9 minus x. Okay, so that's going to give us our limits of integration, 0 to 9. So we do the first integral with respect to y, plug in 9 minus x and 0, and plug the second one in. And you do have to do these in order. You can't split these up. And I'm just going to jump to it. You should be able to do those double integrals. Minus 243 over 2 will be the final result. Let me make sure I didn't miss anything here. I did. So there is one more thing. When it says downward orientation, that's going to pick up a negative sign. So there should have been a negative sign on this integral all along. And because you're going to get a positive 243 over 2 out of this, but the downward orientation adds another minus sign, which will show up at the very end. Okay, and that'd be problem 7. Okay, in problem 8, we have a mass problem. This is the mass of a thin funnel in the shape of a cone. Z equals x squared. So it says z is equal to the square root of x squared plus y squared, where z is going to vary between 1 and 4. And then gives us a density function, xyz is equal to 11 minus z. Okay, so the first thing we're going to do is we're going to say that we want to replace this with r of x and y. So r of x and y is going to be x, y, and z, which is the square root of x squared plus y squared. And then there's a form of this that I haven't shown yet, so let's try it, that says we can find the double integral by taking rx cross with ry and finding the magnitude of that. Well, rx is going to equal 1, 0, and this would be, we saw this one before, x over the square root of x squared plus y squared. And ry is extremely similar. It's going to be 0, 1, and y over square root of x squared plus y squared. And when you cross those two, a lot of this goes away. And then when you take the magnitude, it's going to look like, very similar to what we saw, it's going to be 1 plus, it's going to end up being x squared plus y squared over x squared plus y squared, which equals 1, so it's the square root of 1 plus 1, which is 2. So I did skip the cross product here, and I've only shown you part of the magnitude equation, but we've seen one very similar to this, so I think you can get there. Then we just need the mass equation. The mass equation is a double integral over the surface of our function with respect to x, y, z times the density function. So it's going to be, oh no, this is the density function. So the mass is just the double integral of the density function with respect to ds. Okay, so this is going to be, but basically we're going to change this to the double integral of, we're going to end up changing this to the density function in terms of r and theta times the magnitude of the cross product of Rx and Ry. And then we're going to have, we're going to leave this as x and y first, I should put it that way, times this dA. And then we're going to change it to r and theta. So I jumped the gun a little bit there. This is still x and y. Okay, so we're going to get rid of z. So the density function we're going to write not as z, but we're going to write it as 11 minus z. Oh, I just said we weren't going to write it like that. We're going to write that instead as the square root of x squared plus y squared. That's what z is. Times this cross product, which is just square root of 2, and then we're going to have dx dy. But it actually turns out to be a little simpler if we change this to spherical, or I should say polar coordinates. So in polar coordinates, this whole thing is just the square root of r squared, which is r, and then dx dy is going to be r dr d theta. So we're going to get 11 minus r times, let me pull the square root of 2 all the way out in front, times r dr d theta. And our r is going to go, z is r again, so r is sandwiched between 1 and 4. So we're going from 1 to 4, and theta is again going to go from 0 to 2 pi. And this is a pretty simple antiderivative to do, so I trust you can get this. You're going to get this equal to 123 pi, and then that square root of 2 will carry along for the ride. So that will be problem 8. Okay, for problem 9, we're given a hemisphere problem. Gauss's law to find the charge contained in a solid hemisphere. Now when you see things like hemispheres, think spherical coordinates. So we have a squared is the same as rho squared. So rho, the radius of the hemisphere is a, just a constant here. And our electric field, E, in x, y, and z, is equal to x, y, and 5z. And we're going to solve for z squared here. I don't want to do that. Let's not do that yet. So we're going to change E to spherical coordinates. So E, it's kind of long, and phi and theta is equal to A, so you'll recall spherical coordinates as rho, sine phi, cosine theta. So it's A sine phi cosine theta, that's what x is. Y would be A sine phi sine theta, and 5z would be 5, z is A cosine phi. Okay, now part of this is we're going to calculate the partial derivative with respect to phi crossed with the partial derivative with respect to theta. And in spherical coordinates, we call that t phi and t theta, kind of like using r when we do polar coordinates. So t phi, the partial derivative of E with respect to phi would be A cosine phi cosine theta minus A, no, this is phi. So it's still A cosine phi sine theta. And this one gives us minus 5A sine phi. Okay, then we're going to find t theta, which will be the partial derivative of those with respect to theta. So it's minus A sine phi sine theta. This one would be A sine phi cosine theta, and this one's 0. Very similar to the one we did before. Then when you cross product those and take the partial derivative, I'm going to do both these in one, not partial derivative, you take the magnitude of that vector, you're going to get, actually I didn't do that. Let me show you what the cross product is. So the cross product is equal to a squared sine squared phi cosine theta, a squared sine squared phi sine theta, and the third term is a squared regular sine phi cosine phi. So careful, that last cosine is not a theta, it's a cosine phi. Okay, then we're going, so this is a vector still, and then we are going to, and then you do take the magnitude, so I haven't done that, and then you will multiply it by the E vector in terms of this, and you'll get the limits of integration. Let me write it all out. You're going to get 0 to 2 pi. Again, don't have time to show every step. Setup, and then a few steps, and then conclusion. You should get a cubed sine cubed phi plus 5a cubed sine phi cosine squared phi. D phi d theta. So there are quite a few terms that do go away, and you're left with these two terms. Let me just double check it one more time. That's correct. And when you do the first antiderivative, you should get 7/3 a cubed d theta, and then when you take the antiderivative of that and plug in theta, you get 14/3 a cubed times pi, which is the answer right there. And then there's a charge term, electric charge term on there, but they already factored that out for you. Okay, so that's problem 9. Okay, so problem 10, last one, we have a conductivity problem and a heat flow situation. So we have, they give us this conductivity K is 4.5, and they give us U, which is going to represent the internal temperature, XYZ, is 4y squared plus 4z squared. And we've got this across a cylindrical surface, so it says y squared plus z squared equals 6. And they tell us x should be bound between 0 and 4. Okay, so where do we start with this one? Well, we're going to find the thermal conductivity times the gradient of U. So the gradient of U is pretty simple. It's just the partial derivative of each of these terms, but then we're actually turning into a vector. So it's going to be 8y, now it's in the I direction. And it's going to be, there is no y term, so there's no, so it's 0j, and then it's going to be 8z in the k direction. So that's k times the gradient of u, and we're going to have we're going to write this as, we're going to write r, this vector, in terms of x and theta. So we're going to parameterize this, and that's going to be x. And from this 6, if we take a square root to solve for z, we're going to get square root of 6 times cosine theta and square root of 6 times sine theta. That'd be the parametrization of this equation here. Okay, now we're going to find Rx crossed with R theta magnitude. So partial derivative of x is just going to be 1, 0, 0. Partial derivative of theta will be 0, and then square root of 6 sine theta, negative square root of 6 cosine theta. If you take a cross product and the magnitude, you should get, oh, I didn't take the magnitude in this, I just did the, well, let me actually show that step. So it'd be the magnitude of this vector, cross product should give you 0, negative root 6 cosine theta, negative root 6 sine theta, and when you take the magnitude of that, you're going to get root 6 cosine squared, root 6 squared sine squared, which is going to be just 6, and then you'll factor out a cosine squared sine squared and get 1, so this whole thing is just going to be 6. Okay, so then we're going to take it's going to be the antiderivative of, when we plug all this in, 0 to 4, 0 to 2 pi of negative it's k del u dotted with ds, and that's going to turn out to be 0 to 2 pi, 0 to 4 of negative 4.5 times negative 48, which is this 6 times these 8s up here. So we get, this is, and then it's dx d theta, and then we do this antiderivative of the first one. You should get 864 d theta. The antiderivative of that would just be 1728 times pi. And that would be problem 10 and complete section 16.7.